Assalamualaikum warahmatullahi wabarakatuh and good day again. So this is the third part of the contaminant transport video. Okay, now let's see the dispersion. Okay. Okay, previously we know that in the micro scale level, contaminant is defined by the average groundwater velocity. So in this dispersion, so we want to look at the micro scale. So how the dispersion is flow, what is the velocity from point to point. It is either can be low or higher than the average velocity. So in the micro scale, we can see the differences because we have a different pore size. We also can see the effect of the path length and also the friction between the soil pores. Okay, so this is what it means by the dispersion in mechanical dispersion. So in the contaminants contamination process, so A, B, and C. Let's say A, B, and C is the pollutants or the molecular. So A can choose a quite easy path compared to A, B quite difficult, and C maybe the longer or the lengthen the length of the path of the contaminants. So this already represent different speed or different velocity of each molecular of contaminant. This is called as a hydrodynamic mechanical dispersion or simply dispersion. So we can have a longitudinal dispersion and we also can have a transverse dispersion. So this is how example the contaminants having a hydrodynamic dispersion looks like. So the length is quite variety, so they can disperse here or there and so on. So how to consider the dispersion in the calculation? So we can opt the longitudinal dispersion by defining the dispersion in the longitudinal equal to alpha L times the velocity. So alpha L is the longitudinal dispersivity, and Vs the average seepage velocity. So similarly, for transverse dispersion, we also can define dispersion d sub t equal to alpha t, which is represent the transverse dispersivity. So this alpha can be defined actually in the laboratory. Okay, but before we go to the slide of defining the alpha, okay, let's see that the mechanical dispersion and also diffusion usually occurs together. So combine their expression, so we can get d sub L star and also dispersion transverse star, or I would like to call as an effective or diffusion dispersions in the transverse and also longitudinal. Okay. So we also can include the toticity effect in the diffusion. So you still remember that. So that we can define the alpha L and alpha T, the dispersion coefficient from the laboratory. Okay. Okay, this is the laboratory testing for dispersion coefficient. Okay, by defining the pore volumes U, we can also suggest a coefficient and an equation for dispersion in one-dimensional continuous injection. So the concentration of the contaminants equal to initial value of contaminant divided by 2, arrow function to the length and also the seepage velocity times the time divided by 2 square root of uh, dispersion and diffusion in the longitudinal times the time. So let's see one example that combine the dispersion and also diffusion. So okay, we have a chloride solution for 1000 milligram per liter has passed through the column test, and the length of column was 0.5 meter and the seepage velocity Vf is 0.005 meter per second. So try to calculate the value of longitudinal dispersivity A, alpha L, for the soil in the column. So it's given you the time, I think 200 seconds, 400 seconds, 700 and 900 is time, and concentration 2.5 and 450 at the last one. So how to calculate? So by using the coefficient of dispersion, so we know that C is 1000, L is 0.5 here, Ds is 0.005. So this L star is diffusion, dispersion and diffusion is 1 times 10 to the power of minus 5. So we actually assume this. Okay. So by using some table for specific time, we can calculate the U, and then we calculate the component inside the bracket. So we arrow function using the Excel and reverse the arrow function here and divided by 2 and calculate the C. So at respective time we can get some value of C, different value of C. So this value times and also C is plotted in the graph. So we have a concentration, we also have the U was equal to B times T divided by N. So we can have a data. So let's solve for the alpha sub S, the dispersion longitudinal. Okay. So go back to the basic equation. So we get the alpha sub L equal to 0.11 meter. Okay. Besides the laboratory testing, we also have a field test for dispersion coefficient. So we can get the some idea of the contaminants occur. However, both lab and field testing does not provide accurate values of the dispersivities because we doesn't really know what happened inside the ground. For the field testing, we can use the observation wells to locate the contaminant at different locations, and from there we analyze the how far the transport has been occurred. Okay, this is example of the field measure value on the longitudinal dispersivity with the function of the scale of measurement. So they plot some ideas of the alpha L. Okay, for the just now is we only discussed the one dimensional. So for two dimensional flow fields, so of course we have to have two directions, x and also y, the longitudinal and also transverse. So we can also have a simplified version of the equation. So we know the initial x, the starting point of the contaminant occurs. Also y naught, x naught, and we want to know how far it goes. So we can check later at the end we can define how much the concentration occurred at certain location at certain time. Okay. So another example of the dispersion. So this is the equation. So it asking how long. This time is we want to check the time. So how long will it take for the chemical concentration to reach 100 milligram per liter at the drinking water well location? So we assume advection and dispersion control the mass transport. So we know the I value, K value, porosity effective, and also dispersivity for the longitudinal, and also the initial concentration. So when the concentration achieve 100, how far already the time? So just use the equation. Just now R is actually R equal to 1, means there is no retardation, no no sorption. Okay. So that's why easily we fill up the space, and we do trial and error, so we can get T will be 19.3 days to achieve 100 milligram per liter um, of the concentration. Okay, okay, we already know that we learn about advection, diffusion, and also just now dispersion. Okay, all of these transport manners actually can be totaled up as a total contaminant transport migration. Okay, so the transport equation can combine for the advection, diffusion, and dispersion. So, and we just now consider one dimension to discuss. So all the flux is J sub A, advection, J sub D, diffusion, and J sub M for the dispersion, mechanical dispersion. So we know J sub A is porosity times U times C, and this is D effective, diffusion times the porosity, and partial derivation of concentration to the X, and also uh, dispersion, mechanical dispersion times the porosity, and also the partial concentration to the X. So we can have simplified version of the flux when we assume the hydrodynamic dispersion dH equal to the diffusion and also dispersion. And we know that diffusion is totality times the initial diffusion plus the alpha L times the U. Okay, and next, so we know that in general, so we have a changes in contaminant mass with time, and the flux is there, so J, but flux is actually not a stable one. It's quite uh, in and out. So sources and sink, they have a source and they also have a sink, S slash S. So when we substitute all the equations, equation 3 into 2, the component of concentration total in total mass, so we can get a new equation, and we know we also can have a diffusion condition, K sub D, and we can get a new function. So we know sometimes also there will be retardation factor, so R sub D, so R here, and usually retardation will make the transport become slow. Okay, so the solution of equation 8 just now can be solved for variety of boundary conditions, and usually in general it predicts as a spreading Gaussian cloud, which looks like in this graph, Gauss, Gaussian graph. Okay, so this is 1D. You can see the effect of retardation. When increased, it becomes slow. And 1D for others, 2D solution, 3D solution, and 10. Okay, that's end the contaminant transport chapter topic. So next we will discuss some of the exercise and see you in the class. So I think that's all. Assalamualaikum warahmatullahi wabarakatuh.